Hey everyone, given that a lot of people liked the video where I read out my math IA, I decided to read out my physics IA, which somehow got 24 out of 24. I got a 7 for it, and yeah, that really helped me nail that 7 in physics. But first I want to preface that in terms of the physics IA, mine is going to seem like really out there, weird, and creative. But just to let you know that every physics IA is different. Some physics IAs I like take really boring, simple concepts and then just go super in depth with them, and then they get really high marks. It doesn't have to be interesting. You don't have to do something you're super passionate about. You just have to show that you understand physics and that you know what you're talking about. So if you're gonna look at my IA, I recommend you to also read other IAs. I recommend you to read the ones that IB puts on its website. Those were really helpful in helping me do my IA, because it gives you perspective from what multiple different physics IAs would look like. So there's generally 3 types of physics IAs that you can do. You can do an experiment, you can do a data analysis, or you can do a computer simulation. I don't know why. After I've done so many physics experiments in the lab, I was like, okay, I never want to go in the lab again. So I decided to do a simulation mixed with a more simple real-life situation physics experiment. So for my physics IA, yeah, I did a simulation. To briefly go over what simulation and what kind of concept I was exploring, how I found it was that I saw this video by 3 Blue 1 Brown, in which he was trying to show how, I can't really explain it, you just kind of have to watch the video. So basically what it's saying is that if you have a mass of 100 kilograms and then 1 kilograms, and then they're sliding against each other and colliding against the wall, if it's 1 to 100, you're going to get 31. And if it's 10,000 to 1, you're going to get 314. And if you have 1,000,000 kilograms to 1, then you're going to get 3,141. Actually, those digits are the digits of pi. Okay, so moving on. So yeah, basically what I do in the introduction is that you start off with an interesting fact, which leads to your theory, which leads to you being inspired to create a research question out of that theory. Now the introduction is really important, because the introduction is going to be where you're going to capture the interest of the examiner. It's where you're going to kind of lay out what the style of your IA is going to be. So in your introduction, if you've got like a bit of English errors here and there, if you like spell things wrong and you say things a bit weird, that's going to be your first impression for the examiner for the entire rest of the IA. If he sees that in your first introduction you are like saying things funny with funny English and not spelling things right, he's going to keep that in mind when he's reading the rest of your IA, knowing that this kid can't say things right. That's not to scare you, that's just to warn you that introduction is quite important. That doesn't mean it's hard to write. If you follow my structure, then you should be fine, because you really want to make sure what you say in the start sounds good. You know what I mean? Okay, so in this next part of my IA, I lay out the aim of my investigation. And this is really important into centering and telling the examiner what your IA is about and what you are going to do. In this aim, you're basically going to lay out what you want to do and what you want to accomplish. It kind of lays out the foundation for the rest of your IA, because the examiner knows, okay, this guy's going to do this. And so in my aim, I say that my aim is that I first want to attempt to do this experiment on an air track, and then I want to expand on that by using different simulations in order to further test the necessity of elastic collisions in my experiment. And then I tell the examiner, first I'm going to do this with a simple code, and then I'm going to use a more complex code to show how the value of pi is actually computed. So in this little aim right here, I'm basically just telling them exactly what I'm going to do, and because my IA makes sense, the aim makes sense, and it gives the guy okay, this person knows what they're doing kind of feel. And then next I move on to background. So my IA, one issue with it that I faced at the start was that it was really theoretical and math based. So I needed to show how physics was related to the issue. So in this part, I try to outline the background for understanding collisions, and I lay out the equations that I'm going to use. So right here, as you can see, first I'm talking about the floor and friction, and I describe the mathematical significance of the floor. Then I lay out the use of the equation S equals VT, which is going to be important. Then I lay out the conservation of energy equation, which is going to be really important as well. I am also making sure that I label all of my variables. As you see, m equals mass of object, big M equals mass of larger object. I am also making sure that I'm consistent. I'm not going to use big M for mass of larger object and then later use it for something else. No, I'm making sure that I'm always using a big M for the mass of a larger object. Next, I outlay the conservation of momentum equation that I'm going to use. Alright, so after conservation of momentum, I talk about velocities after collision, and this is a really important in which I try and take all of the equations from before. This is like the climax of my equations, in which I'm taking all of the equations, putting them together in order to get an equation for what the velocity of the blocks should be after they collide. And when you are writing your IA, you need to make sure that you have those clear derivations out there. So I'm not going to go through it because it's complicated, but basically here I'm just like taking all of the equations I had before and deriving the equations that I need to explain my IA. So I'm going through the derivation, I'm subbing in, I'm showing the steps, because this really shows my understanding. And then eventually I get to an equation. After the balls collide, the velocity of the small ball should be this, and the velocity of the bigger ball should be this. And then after that, what I'm going to do is I'm going to show how those equations are important and how they are basically calculated in the simulation. And then in this part of my IA, I'm basically going through what the simulation would do for me. Having done all of these equations, and then what I'm showing here is that I could basically figure out the number, like figure out what's going to happen in a given space of time, like through hand. Like I can do it like through going through the equations and plugging in all the numbers and doing it all like that. But when you get up to like 314 collisions, that's going to be a lot of calculations that you're going to have to make, and it's much better to let the simulation do that instead. But in here I'm showing my understanding of that simulation by going through what the first collision would look like. So here I have a diagram. So first the block goes off at 1 meter per second, and these blocks are a ratio of 1 to 1. Hits this block, then according to the equation that I just laid out, it will move off with a velocity of 1 meter per second. The green block will have a velocity of 0. Then it will hit the block, change to negative 1 meters per second, then return back to the green block, hit that block, and go off at 1 meter per second. Now all of this was calculated through my equation. So basically what I'm doing here is just laying out what is happening in the simulation, because I can't do this for when there's 31 collisions. That's just going to be too confusing. And yeah, and then I do the count and I find out that the total number of collisions is 3, which is the first digit of pi. In this next part of my IA, I attempted to conduct the experiment in real life. And what I did is I used a glider, and then I used 2 sliding blocks. However, they were different sizes, so I had to add some weight onto one of them. And then I used Logger Pro. I let one glider hit the other, hit the wall, and then come back and hit the other and go off. The importance of this was to show like that I actually did an experiment and stuff. I originally wasn't planning to do this. My physics teacher suggested that I did this. So here is just me explaining what I was actually doing. I'm not going to go into that. This is also important because it gave me a chance to talk about variables, which is a really important thing to discuss in your physics IA, and it's really going to get you those marks. So when I do my variables, I talk about the independent, dependent, and controlled variables, but then I also make sure on the side I talk about the limitations. So in this table, this is a nice way to lay it out. If you're struggling to figure out how to organize and talk about your independent variables, this is a really nice way to do it. So here on one side I have independent, and then I have like the type of variable, and then on the other side I outline what that is, and then on the other side I talk about what the limitations of that are. And then I do the same for the dependent variables, and then I do the same for the controlled variables. And this is really important and will really score you communication points because it's like really nicely organized and it's easy to follow. I would say this is better than having it all in like a big chunky paragraph, because then that's difficult to follow. What you gotta know here is that examiners are incredibly lazy. They're checking many physics IAs at a time, and they're not that smart. So if you can lay out your information in a way that's easy to read, it's organized and it's concise, then that's going to score you more points because it's going to be easier for the examiner to give you those marks. Okay, and then over here I just have some data collection, really boring stuff. It's just my numbers that I took. So what I use is I use Logger Pro. I took a video of it, and then I was able to from that video calculate the distances and velocities of the objects moving. That's boring. And then what the point of this experiment was to show, momentum is hard to conserve. So I found that in the first trial, only 23% of momentum was conserved. In the second trial, 33%. And then the third trial, 44% of momentum was controlled. And the point of this is to show I can't actually do this experiment in real life because it will be impossible because momentum won't be able to be conserved. If it's too much, you can put it in the appendix, but it's really important that you include at least some raw data because it shows that it makes the examiner think you actually did the experiment rather than just make up the graph. And then after that, I present my graphs, so I'm not going to go into them, but make sure that you have labels. As you see here, I have a title, my y-axis and my x-axis labeled with the unit in brackets. That's also really important. In order to gain communication points, you want to label all of your graphs. So as you can see here, for graph 1, I've got that labeled, and that's really important. And secondly, I also have a velocity graph, which I use to show the decrease in momentum as each collision happens. So each of these dots, I'm not going to go into it too much, but each of these dots is like the total momentum, and I just show that with each collision, the momentum just shoots right down until 0. So it's nice to color your graphs and then label them correctly so it's easy for the examiner to see what's happening. I also have little diagrams here where I show what is happening as well so that you can also easily follow it. And then I show how momentum goes down over time. So I'm not going to go into the details of this. What the message of this part can be is that when you're making graphs, be a little bit creative. Try and make it interesting to look at, make it easy to look at. Don't make it really confusing because graphs can be really confusing. And the examiner doesn't want to spend ages trying to figure out what your graph means. They want to just be able to look at the graph and be like, oh, okay, cool, next. They don't want to have to be there what's this? And make sure you have clear photos. So when you're taking a screenshot of it, make sure you go full blown on the laptop and then you click it rather than just doing a small little screenshot of it, if you know what I mean. After that, then I come to the conclusion of my physical experiment, and the point of this is to wrap up my physical experiment so I can move on to something else. Then I move on to the next part of my IA where I try and experiment with simulations. So if you are going to do simulations, a good thing to show personal engagement is to talk about how and why you picked your simulation. You don't want to just be like that dude that just randomly picked their simulation for no reason. So in here, I talk about my quest to find the simulation. I talk about how I looked at many different simulations, but finally I settled with 2 simulations that satisfied the criteria that I needed. I'll go into discussing what those simulations are, where they're coming from, and why I want to use those, why I'm using 2, and really explain why this simulation is valuable. Because if you just pick a random simulation and you don't explain where it came from, then it's just gonna be a bit weird. It's better to go in depth a bit. Then, this is good for personal engagement. I realized that there was something different between the 2 simulations. They were actually using different equations. One was using 16 times 100 to the power of n. One was using 16 times 100 to the power of n. Also, another was using 100 to the power of n without the factor of 16 in it. And I did some research and problem solving thinking or whatever, and I figured out why this was the case, and it was actually just because the simulations were actually counting different things. I outlined that in my IA, and that was really good for personal engagement because it shows I just didn't take the simulations at face value. I actually compared and analyzed them and came to a conclusion about what I need to do because the simulations actually have different equations in them. Then, in order to further develop my understanding of the simulation of what's happening, what I did is I actually took the code of the simulation that I was going to mess with and explained what the code was doing and how the code was using physics. If you're using a really complicated simulation, you don't have to do this. But for me, this was interesting because I was exploring how the physics calculations were being translated into code. So here I will have bits of code, and then on the side I will have explanation of the code and how it relates to physics. And also because I just organized it nicely so that I had code and an explanation, code and an explanation in this nice table, that makes it really easy for the examiner to read, rather than just me outlining in a huge chunky paragraph what I was doing and stuff. This makes it simple. The examiner doesn't really even have to read it that carefully to know what I'm trying to do. So be creative with your communication styles, use boxes, use tables, don't make everything into huge chunky paragraphs. It's not an English lit essay, and yeah, that'll be easier for the examiner to read and give you the marks. After that, I actually did the simulation to try and calculate values of pi, and I was actually able to achieve that. As you can see, I did run into many system errors with it, and I had to keep decreasing the DT, which I'm not going to get into. And here I just kind of explained that. I explained what I found. I explained that I was able to calculate the values of pi, and that all went pretty well. But I do address the fact that there are limitations in my simulation and that I can't really go past a certain number of values. And I outline why that is. It's because this code is too simple and there's not enough like space or whatever. I can't really remember what happened, but yeah. And then I go into the next part of my investigation, in which I'm trying to see how much momentum can be lost until the values of pi cannot be computed anymore. In the code I added a scale factor, which meant that like each time the balls would hit, they would decrease their velocity a little bit. So each time they would hit, you know, it's supposed to be like a big ball hits this ball, all of the momentum is given away. But what I rewrote in the code is that I made it so that the big ball would hit the small ball, and then the big ball would like lose a little bit of momentum. It wouldn't fully transfer. And I kept doing that to bigger and bigger amounts to see what happened. And in this graph, I basically show the point at which the simulation broke, and the simulation didn't calculate the value of pi that I wanted. So as you can see here, we could get about 11% of elasticity loss before the simulation broke and you didn't get the value of pi that you wanted. But then when you change the ratio to 100 to 1, as you can see here, you can only get about 0.23% of elasticity loss before the simulation breaks, which is a huge difference. Now, I'm not going to go into the details of this, but basically what I'm showing here is how the simulation breaks over time. Basically what it's showing is that when that thing goes down, that indicates a point at which the number that you're trying to get, the 3141, cannot be computed anymore. And then after that, I draw conclusions from this graph. Basically, I show like what meaning this graph has, what this graph means, what it entails, and I just show I just talk about like what happened. I draw conclusions, you know. I'm explaining what these graphs mean, what they mean, and what they're trying to tell us about the physics. Then after that, I move into exploring the second simulation that I did. And in the second simulation, I try and use the diagrams created in the simulation to explain where the value of pi came from. So I'm basically doing an analysis of the simulation and explaining why does the digits pi come up in my own words and through my own analysis. So I'm not going to go through this because this is really confusing, but yeah. I do a geometrical analysis, but I felt it was important to add because it shows my exploration of the subject. It shows my understanding, and you know, it finally brings us to a conclusion of why the value of pi is even calculated. And also another reason why adding this analysis is helpful is because it sheds light on why you cannot lose elasticity in the experiment, and why this experiment can definitely not be done in real life. And yeah, and that's basically the conclusion that I come to. I take the knowledge from simulation 1 and the knowledge from simulation 2 and the knowledge from my real life experiment, and I show what I found from that. And then of course I have my bibliography, in which I reference with bracket points. So if anyone wants to know how you do a bibliography, this is how I did it. I feel like this is the simplest and most straightforward way. I find footnotes confusing, and in-text references is also confusing. So what I would do if I wanted to reference something, I would put in brackets number 6, and what that would refer to is number 6 here, in which I have the MLA format over there. And also additionally, I did a lot of the drawings by myself. I created them with Photoshop, and so when you are labeling those drawings, for example graph 5 and graph 6, I didn't reference these here, and I didn't reference them because I actually made them myself. But it's important to tell the examiner that, so if you do make a figure by yourself, you should reference somewhere that this is made by the author. So what I did is that I have this little note here that figures 1A, 1B, 1C, blah 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 are made by the author, and also graphs this, that, and the other are made by the author, to show that I didn't just steal this from the internet. That's all I have for this video. I hope that helps anyone who wants to see what an example of a physics IA looks like. I feel like this is probably my best assignment that I did, out of like everything the IB. I was quite happy with the result. But this is only one example of a physics IA. That's the thing about the physics IA. You can pretty much do whatever you want. You don't have to be that complicated. I know people who did something really simple, like, you know, like bouncing balls, but then they get like full marks. I did manage to get full marks, which I was really happy with. Even the examiner marked it and I got full marks. That's partially because of my creativity. It's because I like really tried to explain what I was doing. I didn't skim over stuff. I labeled everything correctly. I really went into depth. I tried to really show my understanding, whilst also keeping it condensed. And if you want some just like general help with your IB, if you want some help about like anything to do with the IB, message me. I know things are tough at the moment, but we will get through this and we will push through. That's all I have for today, so see you around and thanks for watching. Bye!